introduce our last speaker for this term, David Saltman from the Center for Communications Research, and he'll speak on lifting and mixed characteristic.
Thank you, Zinovi. Before I start my real talk, I think that this was a good moment to thank the three organizers, Kirill, Zinovi, and Philippe, for organizing this seminar. This has been wonderful, and I particularly remember that in the midst of the COVID lockdown, it was basically a lifeline, and I loved it. So I'm going to give you a round of applause. All right. Lifting and mixed characteristics. So let me start off with my abstract because it's easier to do that. In, I believe it was May, Suresh gave a talk where it was a talk about H3 of function curves over global fields. And in the talk, he had, I remember clearly, he had to choose elements, but really what he was doing was he was specifying cyclic extensions of degree P with various properties. In the first case, a half a dozen properties, and in the second case, a dozen properties. And what it seemed to me when I read the paper, this is not work I did since May, I've known about this work for some time, was that what he was really doing was using, without writing down, a sort of a generic Galois extension for Galois extensions of degree P, cyclic Galois extensions of degree P, but which was characteristic free. It was mixed characteristic. Characteristic P, characteristic 0, and other non-P characteristics, but finite. And so I thought about that, and I tried to figure out basically what he was doing. And that's what this talk is about. It starts with actually a polynomial that fits the bill, and I'll go on from there. I want to say at the beginning that the polynomial, though I will show you what it is not as intuitively interesting as the Galois action. So that's the last line of my screen. Sigma of x equals rho x plus 1. That's how the Galois group acts on the roots of, or a root of that polynomial. It's not symmetric. And that is what will turn out to be important. Later in the talk, I will show you how I and maybe some other people should have been able to write that equation down right from the beginning, but that's not how I did it. And then basically, if I have a description of cyclic algebras, then I get of cyclic extensions, then I get a description of cyclic algebras. Given that description of cyclic algebras, and given that it's sort of characteristic free, it makes sense for me to go back to what was my thesis and look at what I did there to turn a cyclic degree P extension as a Maya algebra in characteristic P into a differential cross product. And I do it here too. And then at the end, if there's time, I'll talk about the ideas that seem to arise when I try to generalize from P to P to the N. All right, so let me review. You start with a polynomial ring over the finite field of P elements, FPT, and you write down the Artin-Schreier, generic Artin-Schreier polynomial for that, x to the P minus x minus t, and you define the Galois extension defined by that. In characteristic P, without any condition on T, this is CP Galois, and it's also universal. If I have another characteristic P Galois extension, I get this one by specialization. You know, you basically map T to whatever you need to map T to. As a consequence of that, and this is what I'm going to focus on, rather when what Suresh needed, is that you get a lifting result. That if I have a Galois extension of T and U maps onto T onto, and U also has characteristic P, then I could lift the Galois extension to U. And that's what that says. I will point out the even more familiar, characteristic not P version of this, which uses Kummer extensions. Instead of x to the p, this is x to the p minus t. I have to invert t, and then I also get a lifting result. But I have to be able to lift units. Since I have t, if it's invertible, mod some ideal, it has to be invertible. So there is that condition that U star to K star has to be surjective. All right, so let me tell you what the polynomial actually is. For the moment, we're going to take the cyclotomic ring, the Z rho. Rho is the pth root of unity. All rings, commutative rings in this talk, well, in this first section of the talk, will be zero algebras, which merely means that there's a homomorphism from zero to the ring R. So for example, any ring of characteristic P is a zero algebra because P is totally ramified, so FP is an image of zero. And we're also gonna spend a lot of time using this element eta, which is rho minus one. It is the prime of zero lying over P. And it's, as I just said, totally ramified. And in fact, that lemma one expresses the relationship, and I need that rather specific relationship that rho to the eta to the p minus one is p times x, where x is a unit in the cyclotomic ring. And better than that, as you're about to see, it is congruent to 1 mod eta, that unit x. I need that specific information. All right, so now I'll start with the Kummer extension, x to the p equals capital theta. I'm going to change variables so that x is 1 plus z eta, and capital theta is 1 plus a eta to the p. And I'm going to write down the equation, x to the p equals theta. And what you get is, as an equation, when you cancel whatever you can, that eta to the p is z to the p plus this polynomial g of z equals eta to the p times a. And because of what I just said about x in lemma one, g of z is congruent to minus z mod eta. So our polynomial, the generalized, the lifted Artin-Schreier polynomial, is z to the p plus g of x minus a. And if I go mod eta, that's just z to the p minus z minus a. All right, so that's our polynomial. And the fact is that it does the job for us. I'll point that g is a polynomial with coefficients in the cyclotomic ring, zero, nothing else. It is not quite always Galois, but we know exactly when it's Galois. So that polynomial, if I start with that polynomial and R is a zero algebra, then that polynomial is separable if and only if 1 plus a rho to the p is invertible in the ground ring. And so, for example, in characteristic P, where eta maps to 0, it's always separable. But then again, it's always the Artin-Schreier polynomial. Then, if it's separable, then extensions with that polynomial are Galois with group CP. And there's a choice of this generator sigma such that and a choice of root x such that sigma of x equals rho p x plus 1. And that and then, as I said, modulo eta, this is just Artin-Schreier, modulo eta, rho is 1, and so this is the Artin-Schreier action. I want to point out that when p is 2, when the prime is 2 we're talking about, then of course rho is minus 1, and this is the action sigma of x equals 1 minus x, which I have known for a long time was the characteristic 2 way to lift Galois extensions, but this generalization I just figured out or realized recently. The other thing that I want to point out that we just did is that whenever I wrote down a relationship where eta was a factor of both sides, I factored out the eta. We're going to do this a lot because I need to be able to operate in a circumstance where eta might be a 0 divisor, and I can't cancel it at the last minute. So I'm going to cancel it pre-cancel it whenever I can. And that requires some, I will admit, unfortunate notation. We'll talk about this funny sum of xy to being really the coefficient of eta when I multiply 1 plus x eta with 1 plus y eta. We'll also have to do the same thing with eta to the p, and then I'll put a subscript p. I will point out that 1 plus x to the p, 1 plus x eta to the p is always congruent to 1 mod eta to the p, and I'll give notation to that. That's p lower start px, and then just so you see that there's some sort of weird consistency going on, I will point out that the rho x plus 1 we've been dealing with up till now is also in this notation x direct sum, x nu plus 1. All right. So then the second question you want to know is, how universal is this extension that I just wrote down with this polynomial? This is the proposition: if I have a CP Galois extension and x is a root, i.e. an image of t, and I define sigma by that relation, rho x plus 1, then I get a Galois extension. And it is unique up to adding in this new way by some fixed element, and then there are the sort of relations. But it is not Galois unless that it doesn't have this polynomial unless 1 plus x eta is a unit. There has to be, you have to invert 1 plus, I'm sorry, I didn't write this down, but I should have written down. It's not Galois unless 1 plus a to the p is invertible. So that is what's true there. Okay, this is the, sorry, I was getting ahead of myself. When is an extension described by this polynomial? There is always an element such that rho x equals, sigma of x equals rho x plus 1, but you don't always have the invertibility I need. The technique I need to do this is sort of this curious thing that, again, I should have realized all along. I mean, basically, we're talking about the group ring over the, so RT mod t to the p minus 1, or R sigma mod sigma to the p minus 1. And if that sigma over the cyclotomic ring, sigma to the p minus 1 factors, and if I factor it as f times g, then you always have in a Galois extension that if g sigma of s is 0, then s is f sigma for some s prime. Another way to say that is that s to f, that sequence is exact. The proof is, it's obvious if you have a normal basis, and after a faithfully flat extension, you have a normal basis. And now this is proposition 2, which I was trying to fold into proposition 1. If S over R is CP Galois, then there is an X with this element, and if 1 plus X eta is invertible, then the polynomial holds. And I want to point out that this is always true if S is semi-local, if R is characteristic P, or if eta is nilpotent, or if eta is in the Jacobson radical, and that those kinds of conditions are what came up in Suresh's work. Okay, as usual, I'm going too fast. If you would like to get rid of the root of unity, I am going to state the result. It's very technical, but I am not going to give you much of a proof of it. So suppose I look at sort of a generic algebra with a generic element over 0, and I let 0 of x naught to xp minus 1, and I let the Galois action of q rho, that's a q rho, not a qp. Q rho over q act on r prime, but I make the x's fixed, and I basically act the way by acting on the coefficients. Then, of course, the powers of rho give you a basis of 0, and so a generic element can be written as the sum of xi rho to the I. And now I have to tell you in this case what I need to invert. what I need to invert is 1 plus this generic element Z rho to eta to the P, take the tau norm of that, which I will point out is just really inverting all of the tau conjugates of that element. And then I am going to write down this horrendous object, which it's just take way too long to justify, this n of Z, which is this, r to the p minus 2 star sub pz, p direct sum, etc. That whole mess, where the delta in that formula is rho to the r minus 1 over rho minus 1. So it's the sum of rho to the r minus 1, and is a unit. And if I form this S using U, that very rather special U, this is of course CP Galois. I've arranged by inverting C for that to be Galois extension. And the theorem is that I've arranged so that tau extends to an automorphism of order p minus 1 on S in such a way that it commutes with the Galois group, and such a way that the invariant ring is CP Galois. And that's not too hard to show, but I will point out that I'm descending over a non-atal extension, so I have to work a little bit harder. Z rho over Z is not atal. And then there is a theorem, basically now without a roots of unity, and arbitrary ring, I don't have a root of unity, and I can lift over semi-local rings. I can lift CP Galois extensions. All right. So that's the polynomial. And then, of course, without the root of unity, I can't tell you the polynomial. I can just tell you the extension. Now, as I said in the introduction, given a new description of cyclic extensions, you get a new description of cyclic algebras generated by xy subject to the new relation, new Galois relation, y inverse is rho x plus 1, y to the p central invertible, a, which is x to the p plus g of x, that's basically our polynomial, central, and 1 plus a to the p invertible. And that is modulo eta, just the normal Artin-Schreier cyclic algebra, i.e. characteristic P cyclic algebra, where one element has the Artin-Schreier relation. Now, this goes back to my thesis, which I will decline to tell you the date of my thesis. By way back in my thesis, I observed in characteristic P, the differential version of degree P cyclic, so-called cyclic algebras, has a wider application. There are theorems that it's more useful. In characteristic P, we define the algebra A comma B as generated by x comma y, with x to the p equals a, y to the p equals b, and xy minus yx equals 1, a differential relationship. Unlike for a cross product with a Galois extension, this algebra is always azimuth, independent. Nothing needs to be inverted. It's always azimuth, which is first of all very nice. And secondly, if I look at the order P subgroup of the Brauer group of R, then in the paper that basically is where my thesis appeared, a joint with Knus and Ojan-Guren, the P torsion part of the Brauer group of R is just a commutative ring characteristic P, is generated by algebras of this form. Okay, so that's why it's more useful. You basically have a much easier sort of way of writing down all of these algebras, and it's not over a field, it's over a commutative ring of characteristic P. Now, let's start with the Artin-Schreier relationship, y inverse equals x plus 1, and change variables slightly, basically stick in xy inverse as an independent element. And what I'm saying here is that if I start with the Artin-Schreier cyclic cross product, which is generated by that first equation, y inverse equals x plus 1, and make that change of variables, then I get the differential version. So this change makes the cyclic algebra into the differential version. It's a bigger algebra because it has xy inverse. And so now what we do is we do the same in characteristic P, in characteristic 0. We take our relationship in characteristic 0, it would have been y inverse equals rho x plus 1. We plug in xy inverse as a new independent variable, and the relationship we get is the one I wrote down here. Xy minus rho yx equals 1, with x to the p equals a and y to the p equals b. And that's the algebra in characteristic 0 that corresponds to the differential cross product in characteristic P. I find that relationship fascinating, if for no other reason that at least I had never seen it written down before as being useful in central simple algebras. But let's proceed generically. Let me take z rho, join s and t variables, and write down the generic algebra with that relationship. X to the p minus s, y to the s, x to the p is s, y to the p is t, xy minus rho xy equals 1. So this is the general algebra, which is sort of a more, it's kind of like a symbol algebra, but it's bigger. First of all, unlike a symbol algebra, it is always a maximal order, even over the prime p or its factors. And so that's useful. And it's asimaya exactly on the set, on the open set defined by inverting 1 plus st a to the p, where those two s and t. So it's a way of lifting my differential cross product, not to the polynomial ring over 0, but almost to the polynomial 0 localized at 1 plus st a to the p. So that was interesting to me. And by the way, the reason why it is asimaya exactly on that open set is that basically it's a computation of a determinant. You look at the standard map, B tensor B opposite maps to end over CB, and both of those are free modules over C, and therefore any linear map has a determinant, and the determinant is a power of that thing times units. And that's what you can prove. And so now you get a surjectivity result for mixed characteristic Brauer groups. I have to assume some stuff is invertible, which is like often the case if it's semi-local or something. I have to assume that 1 plus eta rho, all of those elements are invertible, but then I get that the result that the Brauer group of R maps onto the Brauer group of R mod I whenever surjective on elements of order P. And I haven't given you the proof yet, except it is clear if rho in some version of rho, that is, if R is a Z-rho algebra, then it's clear because basically the mod P, the R mod I Brauer groups elements of order P are generated by these differential cross products, and I know how to lift them, each one of them, and therefore I get I get the lift if I had the rho, if I had the primitive pth root of unity. So what I would like in order to do this, because as you see up till now I've been very, very concrete, is I would like a version of this algebra B over the invariant rings of tau on C, which is just the polynomial ring in over Z in S and T. I don't know how to do that. There's got to be an algebra there. I'm about to prove sort of that there's an algebra there, but I don't know how to describe it. Instead, I'm going to use the co-restriction at the field level. I'm going to take the algebra B over Q rows ST, and I'm going to take its co-restriction. And then I'm going to observe that I know exactly where it ramifies, because I know so much about B. The co-restriction can only ramify on the primes that divide pi, this 1 plus st rho to the p, and those are distinct prime ideals. I take their norm, and then so what I do is I form this co-restriction, and then I quote this very strong parity of branch loci result of Sesnevis. Sorry, I did that wrong, but I apologize to him. Knowing exactly where it ramifies, then by purity of branch loci, I have a Brouwer class. I don't know what the algebra is. I have a Brouwer class mapping to the Brouwer class I defined as the co-restriction, and using that, I can do the lift. And so I could prove the surjectivity on Brouwer groups. But obviously I needed purity. That's another typo. That's purity of branch loci. I needed purity, and of course I needed the strong version because I needed it to be true at characteristic P2. All right. So, not, as I said, not surprisingly, I'm going to go a little too fast, but let me talk about some of the thoughts I have about generalizing to extension to P to the n. And while I'm at it, I'll suggest that one should go back and rethink what I've done already for just Galois extensions of degree P. I point out this proposition because I didn't know it was true. I noticed it in this work, and it's sort of surprising to me that it's true. If I have a ring of characteristic P and I have any P group which defines an Galois extension, then I have a normal basis. Then as a RG module, S is actually isomorphic to RG. That basically says there's a normal basis theorem, and R doesn't have to be anything. Normally in characteristic 0, you need fields or local rings or something. And here it's always true. There's always a normal basis there. What did I do? I went to the end. Big mistake. Okay. Oh yeah, I thought that was there. So I on the idea that you should always give one proof. This is a side result, but I'll prove this one. So to prove this, it's enough to find an element of S that generates S over R of G. So what's special about characteristic P and G of P group is that the augmentation ideal I of G, generated by all the elements of the form G minus 1, it's generated by nil elements. And therefore it's a nilpotent ideal. And since it's a nilpotent ideal, we can use Nakayama to prove. All I need to do is IG of IG times S is also the kernel of the trace. So I know that since the trace is surjective when it's Galois, I have modulo IG of S, it's isomorphic to R. So therefore it has a generator just by Nakayama. Okay, it's a very easy argument. So if it should be known. So let's go back to the Art and Schreier thing we started with. And I want to say that by thinking about this differently and using essentially the normal basis theorem or something like it, you could have known that we were going to lift the Galois action sigma of x to x plus 1 to sigma of x to rho x plus 1 all along. It's the natural lift rather than the way I came upon it the first way is by going through the change of variables that was in Suresh's paper, etc. All right, so let's take R characteristic P, G the cyclic group of order P. So the group algebra is just R of G is just R of T mod T to the P minus 1. And of course, T to the P minus 1 is T minus 1 to the P. So you get a descending series of submodules of S, sigma minus 1, sigma squared minus 1, all the way up to sigma to minus 1 to the p minus 1, and then the next to the last step is sigma minus 1 to the p minus 1 S is R. And that's because sigma minus 1 to the p minus 1 is really just the trace. And so that is, in some sense, the simplest submodule of S as an RG module. And that's not good enough because it's too simple. It has trivial action. So the next simplest submodule is the next one up in the series, which satisfies x sigma minus 1 squared of x equals 0, which is the same as sigma minus 1 of x is in R. So we normalize sigma minus 1 of x to be 1, and there we are, the Artin-Schreier relationship, sigma of x equals x plus 1. So that's why that's a natural relationship. But now we can look at it in characteristic 0. Now RCP is RT modulo t to the p minus 1, which in characteristic of 0 over the cyclotomic ring is the product of t minus rho to the i's, not t minus 1s. So, and what we want to do is lift the tower I had before, which means I can't look at all submodules. I just look at ones that come from this factorization, which I've written down. S contains sigma minus rho to the p minus 1 contains rho to the p minus 1, rho to the p minus 2, dot, 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 all the way down to the bottom. And once again, R is that thing because the next to the last product is actually the trace, as I wrote down. So the next simplest submodule is the one also that's one up from R. It's the submodule such that sigma minus rho times sigma minus 1 S prime is 0. And again, normalizing that sigma minus rho of x equals 1, or sigma of x equals rho x plus 1, which is now, I claim, therefore, the natural way to lift this action, because it is the next one up on this tower that's given to you by the factorization of sigma to the p minus 1. So this shows the way to generalize what I've been doing, at least when I have now rho is going to be the p to the nth root of unity. So what I'm going to do is I'm going to break up my Galois extension into the cyclic extension at the top, and then S over T, and then T over R, which is the quotient of the group of order p to the n minus 1. And I'm going to say, what is the simplest element outside of T? It has to be outside of T if it's going to generate. And the simplest element outside of T is basically, I take the power p to the n minus 1 plus 1 of x, but this is in characteristic P, so p to the n minus 1 is just what I wrote, is non-zero. And this basically comes out to being that if x is in this simple element, sigma of x is x plus y, where y is in T, because y now is a sigma to the p to the n minus 1 of y is 0. So that's fine. And now I want to normalize the way I usually did before. I normalized y to be 1. Y is now not in this R, so I can't normalize it to be 1, but I normalize it to have trace 1. Because by assumption, its trace is non-zero, so now I normalize it to have trace 1. And that is now my new Galois action. Sigma of x is x plus y, where y is in the ring, one step below in the Galois series, and trace of y is 1. And so now that's how I build my Galois extension. I form T of x. I choose an element of T, which of trace 1, I extend sigma, which acts on t, to t of x by setting sigma of x to x plus y. And then it has order p to the n on t of x automatically. And then I write down that. I have another. Yeah. So I have t of x over is cp to the n Galois. Basically, I built up my Galois extension one step at a time by by assuming it for the subcyclic group of order p to the n minus 1 and adding one guy on the top, which I get by adding an indeterminate. And it's an indeterminate, I don't have to invert anything. So that gives me basically, I iterate this and I get an S over FP of x1 to xn, which is CP to the n Galois, and gives all others by specialization. I didn't even bother mentioning it, but once I have such a thing, I clearly also have a lifting property for in characteristic P for CP to the n Galois extensions. All right, so how do I lift that to characteristic 0? I start the same way. I take a sub-extension, which is CP to the n minus 1 Galois. I assume I have a P to the n root of unity, and that my ring R is a zero algebra. In 0t, t to the P to the n minus 1 is, well, it's the product of all the primitive t minus all the primitive P to the n roots of unity times t to all the ones which are not primitive, the product which is t to the P to the n minus 1 minus 1. So the simplest element not in T is take one element of the product on the left and all the others. So the relationship you get is sigma minus rho times sigma to the P to the n minus 1 of x is 0, which you normalize to say that sigma minus rho x is y of trace 1. Okay, so now I have what I think is the Galois action and a way to lift it. It's easy enough to lift elements of trace 1, so that's pretty good. And I proceed as above. I build up my extension in stages. T over R is CP to the n minus 1 Galois. S is t to the x, and I choose a y and t of trace 1, and I extend sigma to s by sigma of x is rho x plus y. This works fine because basically I've guaranteed that sigma has order p to the n. And then I need to invert some stuff. It doesn't work the same in characteristic 0 as it does in characteristic P. You compute, if I take this tau, which is sigma to the P to the n minus 1, and I act on x, I get rho to the P to the n minus 1. That part's good. That's a primitive P root of 1, but it's plus this element h, which is this complicated element h, which is, well, its complications is what's making me work hard. H is this element. I do observe that it is congruent to 1 mod rho minus 1, so that's good. And I observe that I can take its norm, and that is also congruent to 1 mod rho minus 1, and I can invert this element u, which is its norm. So I'm inverting h and all of its conjugates, which is good. And now I form the polynomial ring Tx 1 over u inverted, and that's S1 over x. I have to divide my element x by h, and now tau of x prime is rho x plus 1. So I now have the appropriate invariant ring. It's a localized polynomial ring. S to the 1 over u to the tau is that, where the guy in the middle is the is the polynomial I defined at the beginning of the talk, but I have to localize at u. And then I have to make another assumption about T over R. I have to assume it has a Kummer-like element, such that sigma bar capital theta is rho to the minus p theta. And then I have my full result that Tx invariant sigma 1 over u is a polynomial ring with that weird element theta fx minus t and 1 over u. And f is basically, it's also not monic, it's h to the p times my sort of lifted Artin-Schreier polynomial. But now we have a generic characteristic 0 lift to our characteristic p extension, and it is generic. And so that's as far as I can go now. I have my lifting characteristic p, but I can only lift at this point when I have a primitive p to the n root of unity. And that is obviously what I'm trying to eliminate at this moment. But the difficulties are real. And you know there's going to be a difficulty because of the different behavior of cyclic extensions in characteristic p and characteristic 0. In characteristic p, all cyclic extensions of prime power order extend to bigger cyclic extensions. There is no obstruction to the embedding problem. In characteristic 0, there's an obstruction specified by Albert way back when, saying that there's a norm criterion for when you can extend. So you can't do the obvious thing. You can't easily do this by stages the way I built it so far, because every stage is going to require you to satisfy a norm condition, which is a Savary-Brouwer kind of variety and which is obviously not rational. So you have to do something else, something more along the lines of, well, some of you may remember the characteristic 0 version of what I want to do, where you're looking over Q and you want to show that there's a generic p to the n Galois extension over Q, not over Q rho, and you do it by essentially splitting, adjoining an element which already has the norm condition built into it for all of its sub-extensions and everything. So you got to do something like that, and I don't know how to do it yet. All right, well, I apologize for going too fast, but that's what I do. Any questions?
Oya, do you have a question?
Okay, so is this work?
Yes.
Okay, so go ahead, Uriah.
I just clapped.
Sanovi, did you have a question?
Okay.
Oh, Philippe.
I have a question. Yes. So because in the literature, there is a paper by Waterhouse about uniafi to make a kind of exact sequence, which is a Kummer exact sequence in characteristic outside P, and which is the Artin-Schreier sequence
Right.
mod P. So this is related exactly with the end of your talk. So the fact that there is no obstruction in for lifting to Z mod to make a tower of Galois. I mean to extend to a higher
Right.
cyclic extension in characteristic P when there is one. Okay, so is your work related with that exact sequence of Waterhouse?
Presumably, this is sort of still, I'm still working on it. So I know the sequence you're talking about. That seemed to be mostly about sort of relating the two cohomologies, but I probably should have another look at it to make sure, I give full credit everywhere. But I
Because
will
the
point
thing is
out,
that there are group schemes now.
yeah, there were group schemes there and all. The thing is is that, yes, there was obstructions in characteristic 0 and not in characteristic P, but one was able to get around those obstructions and still have a generic CP to the N extension in characteristic 0 by being careful. So you can get around the obstruction, and that's really the route forward. I assume you can get around the obstruction. I haven't, but I'm guessing you can.
Okay, thank
Yeah.
you.
Yeah.
Any other questions?
Maybe I will ask one. So this reminds me, so I think I spoke before about what I call diversal torsors.
Right.
So they specialize to, well, in the context of Galois extension, you just look on the constant group G and you want to extend to, you want this thing to be completely universal, but would it be satisfactory if it would only specialize up to stuff of dimension, Kroll dimension at most D? Because it should exist. There you can.
Right. I think, because I think I can do full universality, that's what I'm going to go for. And these are simpler than what you were talking about in your thing. I mean, so there's more of a chance I can do it. As I said, my optimism is based on the fact that A, I was able to do it, everything I wanted for cyclic groups of order P, and B, because in characteristic 0, which is where the obstructions are, I was able to do that too, without just not simultaneously characteristic 0 and P at the same time. So, I'm naturally optimistic, so I'm optimistic, but yeah, no, this is right. If they allowed you to title papers by formulas, and they actually don't allow you to do that in journals, the title of this paper, when it comes out, should be sigma of x equals rho x plus 1, because I just love that formula. I mean, it's everything I needed once, and so I love that formula. Anyway.
Thank you.
All right.
I'm a little bit confused now because of what Duri was saying. It seems like there shouldn't be an extension that's completely versal.
Well, it depends on how complete, what you mean completely versal. This is an odd situation. It wasn't completely versal in the sense that I needed to assume some elements were invertible. I didn't have a Kroll codimension condition, but I needed to assume some elements are invertible. And that, that part's okay, because I just, as I built up, without the roots of with the roots of unity, it's not on the archive yet, but it's all well written out. So yeah, it is, I mean, the problem is the roots of unity, not the universality in that sense, is perhaps the way I could put it. And that is pretty straightforward. That, sigma of x equals rho x plus y as the generalization of smaller rho x plus 1 is straightforward.
But
But
the
in
invertible,
order to make that Galois, I have to invert. That's all.
but you invert in the universal space, right? So
I invert in the universal space.
You can still specialize anything without any condition on the transcendence degree or anything else.
I have to be careful, right? It depends on how universal we're talking about. If I'm specializing to fields, sure, because fields have plenty invertible elements. If I'm specializing to semi-local rings, sure, because they also basically have plenty of invertible elements. But it is an obstruction to specializing to anything because I need something invertible.
Oh, okay, that answers my question.
Yeah.
Now I want to ask if there is an example where there is no such invertible element in the thing you want to specialize to.
I haven't found it yet. It's a good question, and it's I haven't worked that way, but it is quite a good question. You know, is basically to write down a Galois extension over a ring in characteristic 0, where you know, I mean, there are plenty of ones which are not Kummer, because this basically, you know, so but this is more general than Kummer, and I haven't written one down that isn't this. But yeah, but it's a good thing to think about.
Any other questions? All right, let's thank the speaker again.
And I will